Hi everyone, I am Raghanya pursuing M.Sc.Ed Physics at RIE Mysore. In this video, I'll be explaining the top-down and bottom-up approaches in the synthesis of nanomaterials. First, we'll look into each of these approaches and then we'll discuss some of the techniques involved in these approaches, and finally, we'll have a comparison of these two approaches. As you will be aware, nanomaterials are a class of materials having at least one of their dimensions in the nanoscale, that is, from 1 nanometers to 100 nanometers. In recent years, we have seen a lot of applications and properties of nanomaterials which are of great use, like drug delivery in medicine, superconductivity in magic twist angle graphene, etc. Such unique properties and applications come from parameters like particle size, geometry, doping ratio, and degree of particle agglomeration, that is assembly. These parameters are controlled by different routes of synthesis and experimental conditions employed. Therefore, a deep understanding of the synthetic approach is critical in order to manufacture new structure with unique properties. There are two major approaches in synthesizing nanomaterials. In top-down approach, we take the bulk form of the material and divide it into nano-sized particles. It is essentially a subtractive process. In bottom-up approach, we take the individual atoms and combine them to form nano-sized materials. This can be regarded as an additive process. These two approaches are not only seen in synthesis of nanomaterials, but also seen in various fields like marketing, psychology, management, and cell biology. Let us now look at the top-down approach in detail. In the image here, you can see one of the nanomaterials which is synthesized by a top-down approach, the nanodiamonds. As I have mentioned before, in top-down approach, we start with the bulk form of the material in macro scale and break it into smaller and smaller pieces until they become nano-sized. You can visualize this process in the adjacent flowchart. The macro material is broken till they are formed into nanoparticles. This approach is inherently simpler in the sense, even though we have different techniques, all of them are concerned with breaking bigger particles into smaller ones. Hence, it is highly favored for large-scale manufacturing. They depend on either division of bulk material or on miniaturization of bulk fabrication processes to produce desired structure with appropriate properties. We already have so many techniques to synthesize bulk materials. We just miniaturize them for synthesizing the nanomaterials in some cases, not all cases. We will now see some of the characteristics of the approach. The starting material is mostly a solid. This process often involves discard of excess materials which leads to some amount of loss. The biggest problem with the top-down approach is the imperfection of surface structure. For example, the nanowires made by lithography are not smooth and may contain a lot of impurities and structural defects on its surface. Another disadvantage of this approach is that it usually results in smaller flakes or particles with a wide size distribution. As you might have noticed previously, in this image of nanodiamonds, the particle sizes are varying widely. They are not the same. So that means the variance in particle size is huge. For this reason, the top-down approach is preferred for the synthesis of thin films and nanoparticles larger than 100 nanometers. We will now look at some of the techniques which comes under top-down approach. The first one is ball milling. Ball milling is also known as mechanical grinding. It is a simple and popular method. Here, materials are grinded into extremely fine powders. It is one of the most important processes used to synthesize nanomaterials. This method has many advantages such as compact design, energy efficient, minimum maintenance, and it is inexpensive and scalable. It works on the principle of impact. The size reduction is achieved through the impact caused when the balls drop from the top of the chamber in which the source material is placed. As you can see in the image, the material is fractured and flattened and are crushed by the rotating ball. The second technique is lithography. Lithography is the transfer of a required pattern from a master slide or plate or mask to another medium. Nanolithography is one of the widely used top-down techniques for the preparation of nanostructured materials. This technique is based on depositing, masking, etching or writing the desired patterns with dimensions of the order of nanometers on a solid material surface. Using this technique, pattern or design can be transferred at once on the surface of the device by exposure with radiation. In this case, it is UV radiation. Depending on the exposure radiation sources, the technique can be classified as photolithography, X-ray lithography, electron beam lithography, or ion beam lithography. Coming to the third technique called as etching. The process of removing a surface layer from a metal or plastic surface through a chemical erosion is known as chemical etching. This process involves one or more chemical reactions that consume the original reactants and produce new species. The chemical used for etching is called an etchant. In this process, the wafer to be etched can be immersed in a bath of etchant. Generally, etchants such as hydrochloric acid, nitric acid, sulfuric acid and phosphoric acid are used for etching. Let us now look at the bottom-up approach. In this image, you can see the scanning electron microscopy of zinc oxide nanowires which are synthesized through bottom-up approach techniques. In bottom-up approach, the nanomaterials are formed from the atomic scale by joining atom by atom or molecule by molecule, which forms clusters which are then joined to form the nanomaterials, as you can see or visualize from this flow chart. Many nanomaterials are synthesized by the interaction of atoms or molecules through a set of chemical reactions which are provided by each of the techniques. These techniques are still under development or are beginning to be used for commercial production of nanopowders. So they are not widely used right now. We'll now look at some of the characteristics of bottom-up approach. The precursor is typically a liquid or gas that is ionized, dissociated, sublimated or evaporated and then condensed to form either an amorphous or crystalline nanoparticle. It has the potential of creating less waste and hence it is more economical. Yet the techniques involved are complicated and precise, hence they are comparatively expensive. This approach produces nanoparticles with fewer defects, homogeneous chemical composition and less contamination. They also produce particles with a narrow size distribution, and for this reason the bottom-up approach is considered more precise in the synthesis of small nanoparticles which are less than 100 nanometers. We'll now look at some of the techniques involved in bottom-up approach. I will not be going into the details of these techniques. They are physical vapor deposition, chemical vapor deposition, salt gel synthesis, electrochemical deposition, atomic layer deposition and hydrothermal synthesis. Now we will compare the aspects of these two approaches. Here is a combined image of both the approaches in synthesizing carbon nanomaterials. The carbon substances are transformed into smaller fragments which are split into monolayers of graphene to form nanoparticles. This is the top-down approach. Alternatively, the precursor containing molecules are combined by ionization and then are condensed to form clusters which are then converted into nanoparticles. This is the bottom-up approach. From these nanoparticles, we can synthesize other carbon nanomaterials like graphene, fullerenes and diamonds. As a way of summarizing, I have included a table that highlights the differences between two approaches. In top-down approach, bulk material is converted into nanomaterials, whereas in bottom-up approach, the atoms are converted into nanomaterials. In top-down approach, the starting material is mostly solids and in bottom-up, it is liquids and gases. And the top-down approach is relatively simple, whereas the bottom-up is hard. It involves complex processes. The top-down approach is cost-effective, whereas the cost of bottom-up approach is usually high. The top-down approach involves more wastage and the bottom-up approach has minimal wastage. In top-down approach, there are high defects, whereas the defects are very few in bottom-up approach. Top-down approach produces particles with wide size distribution, whereas in bottom-up approach, the size distribution is narrow. And the preferred target size is greater than 100 nanometers for top-down, whereas for bottom-up, it is less than 100 nanometers. I hope you found this video useful in learning about the two approaches for synthesis of nanomaterials. Thank you.